Good afternoon, everyone. Welcome to Takeo Tuesday on July 1st. Hard to believe it's already July 1st. Oh my God. I don't know what that means, but I know that means it's flying by. The year is flying by, July 1st. And July 4th will be on Friday. Oh, nice long weekend. Anyways, Brett Zerba here. I'll be moderating today's webinar, and Tony first will be doing the main presentation. Tony is one of the newer trainers at Takeo. We now have 6 of us that are dedicated to training. We do other things too, but training the industry, mostly in North America. But well, Mexico is part of North America, I think, still. And one of the guys is going down there next week, I think. So he's doing some work down there. So we do travel, and we go north of the border as well. But today's presentation is on self-sensing and parallel pumps and a controller for that. And Tony has an enormous amount of expertise in that. Can a couple people type in that they can hear me and see me, or raise their hands or something, so I can, hopefully everyone's hearing me. Uh-oh, nobody's saying anything. Okay, I can hear you. Good to go. Thank you, Jordan. I appreciate that. By the way, today's presentation is available as a download. So there is a handout. The slides are available for you to download from today's presentation. And nobody usually has a problem downloading them, so hopefully that's all easy and straightforward. So like I said, I will be moderating. Rich is on the call as well, Rich Medeiros. So he, thanks, Joe. He will be learning. Rich and I want to learn a lot about this topic.
I'm a passive learner today.
Passive learner.
Passive learner.
That sounds. That's in between feeding cats, right? Or
yeah. Yeah. I had to feed my daughter's cats this morning before work. That means I had to get up at 5 o'clock this morning. Oh my God.
A parent's job is never done, is it, Rich?
It's not. Well, I kind of think of you and Brett as being my new children.
Thanks.
Well, you guys, just like most parents, you guys, the young guys, you're smarter than us old parents.
Yeah. Takeo Thermal Appliance Company, a 105-year-old privately held company. I had the pleasure to have a cookout that Johnny was at the other day, the owner of the company, and he's quite an individual. He's quite the guy. So anyways, I'm not going to spend too much time introducing this here, but I want to get Tony getting right into it. So like I said, I'm going to moderate. So I'll be watching the questions, and I'll break in and have Tony answer them as they come up, or at a good point, as we can see here. So please do ask some questions. So we all understand that, and it's one of the best things there are in this world is when we start asking questions. I'm a firm believer in that. So anyways, other than that, everyone can hear me. They can see me. I talked about the handout, and 24 hours tomorrow, roughly 24 hours after today's presentation, you'll get access to the recording as well as able to download your PDH hour certificate if you so choose. Other than that, I'm going to turn it over to Tony. And Tony, introduce yourself and take it away, my friend.
Brett, thank you very much. Rich, glad to have you on board today too. As Brett said, I'm Tony First. I'm a senior systems engineer in the commercial training group with Takeo. I've been in this industry way more years than we want to talk about. And believe it or not, I'm almost at my 1-year anniversary with Takeo next week.
That's amazing.
Yeah. Hard to believe it's been that.
I can't believe that, to be quite honest. Wow.
But anyway, so today we're going to talk about self-sensing and parallel pumps and let you know how to actually control parallel pumps to do it efficiently and intelligently. So we're going to start out, we're going to talk a little bit about the history of self-sensing, where self-sensing came from, how long it's been around, and that to kind of give you a history lesson. We're going to talk a little bit about the affinity laws. We're going to talk about variable speed curves. We're also going to talk about system and control curves because they're not the same thing. Very similar, but not the same thing. And then we're going to talk about parallel pumps and redundancy and what that really means for your system overall. So hopefully everybody knows this formula. This is the universal hydronics formula, because we have to understand that a pump's job is to deliver flow and transfer energy. And so we use the universal hydronics formula to determine how much flow we need to have based on the BTUs of the system and the delta T that we desire to have. So that's really the crux of everything we talk about within the pumping world. So let's talk a little bit about self-sensing, where it came from, because it's not new technology. I promise it is really not. Self-sensing was developed in the mid-1990s by a company in the UK by the name of Holden and Brook. Holden and Brook developed it using an integrated pump motor VFD combination, and they used it for quite a while in up and through the mid-90s. And it was first launched in the UK and Europe up to 10 horsepower. Over there, they have much smaller pumps because they typically don't do cooling loads the way we do. A lot of their places are heating only, so their pumps naturally a little bit smaller. So Holden Brook eventually got bought, and the company that bought them brought the technology here to North America, and that was in 2002. And this is when it was launched into North America, was in 2002. And that included pumps with unit-mounted drives that had all the self-sensing capability built into them, so we no longer were required to have a pressure transmitter out in the system to tell the pump what speed to run at. So as you can see, it's been around for a very, very long time. This is not new technology. One of the challenges when it was first brought to North America was in Europe, they only have 208, 230 volt, and it wasn't 60 hertz, and it was under 10 horsepower. So that was one of the first things that happened, and that happened pretty quickly. As you all know, VFDs have radically changed over the past 25, 30 years, and they've become a lot more reliable. We do VFDs now up into 4160 volt drives, pretty much anything you can think of. So how do we develop self-sensing? Well, first of all, we have to validate the performance of the pump. So we put it on a test stand, and this is similar to developing a pump curve. But what we're actually going to do is we take the pump and we put it on a test stand, and at the entire curve range, we run the pump out and we decrease the head and increase the head and figure out what the power consumption is at each one of those data points. Because we know that for every flow and every head at a given speed, there is a different power requirement. So we take all this and we map all this out, and that becomes the performance map for the pump. So then we take that data, and we can't just dump a pump curve into the pump exactly. It goes into what essentially looks like an Excel file. This is half of the plot. We actually plot 20 points, so we know 20 different spots on the curve. And we take those numbers and we plot them into essentially what essentially looks like an XY lookup table, if you're familiar with Excel. That's kind of what it looks like. And that gives us the performance map for that entire pump over its entire operating range. So what we have to understand is all this is working on the affinity laws that we should all know. We know that through the affinity laws, flow rate varies directly with pump speed. So 100% speed is 100% flow, 50% speed is 50% flow. That's the real simple one. We also know that head varies as the square of the speed. So the head's going to move up and down as we square the speed up and down. And then this is the one that's really important to understand, is power absorbed varies as the cube of the speed, or the brake horsepower varies as the cube of the speed. This is where VFDs really shine because of the energy save that happens with putting a variable speed drive on fans and pumps. So to look at this more graphically, if we look at this at 80% speed, we have 80% flow. So the left-hand axis, the vertical axis is in percentage. So it's 0 to 100%. And it's also 0 to 100% across the horizontal axis for speed. So if we look up at the very top point in the far right-hand upper right corner, that is our 100% speed, 100% flow, 100% power. Now, as we start to slow down and we drop the speed down to 80%, that's represented by the green line, we see that the flow is now 80%. As we continue down, what we see is that the head is 64%. So the head that pump will develop is 64% of what its design head was. And at 80% speed, the power draw is only 51%. So we've dropped the power consumption by we changed the speed by 20%, but we got a 49% reduction in power draw. Okay, so it's a significant power draw with a fairly small speed change. So let's talk about system curves and control curves and what they really are. So when we look at a system, the one thing we have to understand is that we're dealing with differential pressure. And the thing we're most concerned with is the differential pressure at our hydraulically most remote load. I'm getting tongue-tied today. And that differential pressure is a constant. It's a constant component. Yes, I know it's going to change as the control valve moves up and down, but it's a constant in this entire equation and understanding how the system works. So if we look at this, we understand that a system curve, as we increase the flow rate, we increase the head that is required in the system because we're increasing the frictional losses moving water through the piping system and through all the components in the system. So we go from there, and the control curve is really how self-sensing operates. So if I look at this, this is a representative curve for a pump. And the green bar on the green dashed line on the right-hand side, that is the pump total dynamic head. So that is the head that you've calculated is supposed to be there for the design flow rate. Okay. Then we have two components. We have the fixed component, that is the fixed differential pressure that we have to maintain at the most remote load. And then we have the variable component. We know from the affinity laws that head varies as the square of the speed. Okay, so as we move flow up and down and we change speeds up and down, the head loss within our system is going to change and move up and down. So what we have to understand is we have the distribution piping head loss curve, that is the red line. Then we have the control curve, which is the green line. And the control curve is what self-sensing is actually going to operate to. It very closely imitates the system curve. However, it's additive because it picks up the set point pressure, okay, that differential that we know we have to maintain out in the system. And those two together is how self-sensing actually works, because we know that as we increase and decrease speed and flow, we've got to maintain the same pressure. We've got to maintain the same set point pressure. But we know that system curve, that distribution piping head loss curve, is infinitely variable depending on how much water we're moving. So if I look at a pump curve, forgetting all the set point pressures and all that, what we have to understand is that we, as engineers, we design a system for a given flow and head. What the reality is that the system head, the actual system head, is usually never what the design head is. It's higher or lower. Well, as it moves higher or lower, the system flow rate's going to move across the pump curve to that higher or lower flow rate. It has to, because it has to follow that curve. And so that's part of why we put VFDs on, because we can trim that down to exactly where we need it to be. So if we look, and now we're going to talk a little bit about flow rate and pump speed and where this really all starts to come together. So if I look at this, we used to put differential pressure transmitters in. And so you need to understand where the right place is to put that differential pressure transmitter in, because I've seen them in all kinds of different places. I've seen them in mechanical rooms, which is really not a good place to put them, and I'll show you why in a minute. Then I've seen them out. One thing I see in a lot of engineer specs is 2/3 out the longest piping run or 2/3 out the remote load. And then the last option is at the most remote load. And there's good and bad with all of them. Okay, it depends on where you're at in the equation. Are you the BAS contractor? Are you the mechanical engineer? You know, are you the building owner? The reality is all of them have their pluses and minuses. The one that you don't want to do is the mechanical room, and here's why. So if I look at putting this, and the closer I put the sensor, the differential pressure transmitter to the pump, the less change I'm going to see. So if I put it in the mechanical room, what's going to happen is if I look at my design point, my control curve is going to flatten out because I'm going to get very little change in differential pressure in the mechanical room where the pump is at compared to what set point I need out in the system. Now, what's going to happen is if I get a 50% load, so my load decreases by 50%, but because of where my sensor is at, my system curve gets really, really narrowed down. So what ends up happening is at 50% load speed, my pump slows down a little bit, okay? But it actually only slows down about 20%. So you're not getting the full benefit of having that variable speed drive on there, and you're over pumping the system because you're moving more water than what the system actually requires at a 50% load point. Okay.
Hey Tony.
Yes, sir.
Yeah, so Jacob's got a question, and it pertains to location of the DP. Is the mechanical room for the DP sensor the same as the pump?
Yes. Yes, so if you put the sensor, if you go back, I can get my cursor to cooperate. If we go back to this, to my drawing, if you put the DP sensor here across this pump set, so it'd be from here to here, that's where you don't want it. That is the absolute worst place in the world to put that DP transmitter.
It's the cheapest place, or I shouldn't say cheapest, but there's not as much wiring though, Tony. That's why I put it there.
Yeah, and that's what I usually hear, Brett, is I hear that all the time, is they put it there because they thought that's a good place to put it. Well, it's not, because you end up over pumping the system. You end up spending a lot more pump energy trying to meet that most remote load.
You get no savings. You get no savings from having it. It's virtually worthless.
Yep. So what happens is I get this really narrow turn down band. So I don't get all the benefit of having a pump that'll go from 100% down to 30%. So if I put the sensor out, and the further I move away from the pump, what ends up happening is, so same design point, and we're going to go through the same kind of scenario here. Okay, as soon as I get my cursor back where I want it. Now at 50% load, now you can see that what ends up happening is we end up with a much greater turn down. So now at 50% load, our speed is down to probably 35 or 40% of design maximum speed. So there's a much greater energy savings the further away we get that sensor. And the problem is that in a lot of specifications, one of the things I see all the time is engineers say, oh, I'll put it 2/3 out the longest pipe run. Well, is that really the right place for it? As engineers, we know what we designed our system to. We know where that hydraulically most remote load is. That's where that sensor needs to be. So on your drawings, it's a good idea to show the BAS contractor, I wanted it air handler 25, because that's my hydraulically most remote load. And in that way, you get the maximum turn down and the best performance out of your pump, because now you're not over pumping the system in any possible scenario. So we look at this. So how do we get the best efficiency out of all this? So what we have to understand is that self-sensing, all the things that happen within self-sensing, all of that is contained within the drive. and its component parts. So the power speed curve is loaded in there. All of the parameters for the motor are loaded in there, and everything works as an integrated system. Okay, so you've got the pump, the motor, the drive, everything is all contained in one system. So what we have to understand is, as the system is operating and as the flow rate demands are changing, as valves open and close in the system, and we change the flow rate, the power demand changes. So as we start to close valves, the power demand required by the pump starts to decrease, and so we know we're not operating on the curve where we're supposed to be. So this graphic, this slide's got several builds to it. So what ends up happening is that what we're going to do, okay, so we have our frequency curve, okay, or our power and speed curves, okay, and we know that as we move back and forth on the pump curve, we have a resultant power that goes with it, okay? And so what we're going to do is we build out through this. What we're going to see is that at these different operating points, and there's our control curve and our system curve laid into this for speed curves and power curves. Okay, so you notice speed curves are going from top left to bottom right, and power curves are going from bottom left to top right, because as we move further right on the curve, the power draw is going to go up. Okay, so what happens is we've got all these points plotted. We plotted that pump curve in there. Okay, so we know what all these data points are. And what's going to happen is now we have this true power speed curve that's loaded into the pump and into the controller. As valves start to open and close in the system, what happens is now the pump is not operating on that control curve. The power, speed, and flow don't match. So the controller is going to go, okay, I need to either speed up or slow down to get it back on that control curve. So it's always working to constantly stay on the control curve. As valves open and close, the pump is going to speed up and slow down to stay on that control curve. Okay, and that way, as we start to slow down, now we come back onto the control curve again. And as we continue, what we'll see is that we continue to move through this as demand changes. We just move back up because the power started to change, so we increase the speed back up to stay on that control curve. And that's the real science behind self-sensing. It's not magic, I promise, it really isn't. We're using the basic affinity laws and what is happening inside that pump and motor. So how do we maintain best efficiency? So if I look at what's been industry standard for years and years and years is speed-based staging. The problem with speed-based staging is it's simple. And you cross over the best efficiency points in a pump's operating curve. So if I look at speed-based staging, and speed-based staging is just that. I get a pump, I ramp it all the way up to 90 or 100%, and then I turn the second pump on. When the second pump gets all the way up, then I turn the third one on. And that is speed-based staging. What we really want to talk about is efficiency-based staging. And efficiency-based staging is a little bit different. So if I come up and my first pump, I brought it on, both of them are operating about the same, power draw is about the same. What happens is my load increases. Okay, I need more pump. So with speed-based staging, what's going to happen is I'm going to increase the speed, and I'm still only running one pump. In efficiency-based staging, I'm actually going to start that second pump because I've crossed the best efficiency point for one pump. Now I'm going to start that second pump, and I'm going to run two pumps in parallel. But if you notice, when I look at power draw, if I'm running one pump at almost full speed, I'm using 30% of the total connected power, whereas two pumps in parallel, I'm not even using 20% of the total connected power yet. So I'm using less energy to do the same amount of work. Same thing happens as I continue to move out my load range, okay? I've now turned a second pump on, and I continue to move out. Now I'm going to turn that third pump on. Well, here's what you've got to notice is I've got two pumps running at almost full speed. I'm using almost 80% of the total available power in speed-based staging. But with efficiency-based staging, where I've got three pumps running in parallel, I'm only using 40% of the energy. So I'm almost half of the energy being consumed versus what I am in traditional speed-based staging. And the only time that I ever get to the point where the two of them are roughly the same is when all three pumps are running at almost full speed. Well, we understand that design capacity, design load point only happens about 5% of the time. So why would we want to design a system where the only time our energy is equal is when we're at that design point? We're going to spend most of our life at a part load condition. Doesn't it make more sense to design and operate your system for best efficiency at that part load condition where it's going to spend most of its life? So a real world example, 340 horsepower pumps. This building was done with self-sensing, with parallel and control and efficiency-based staging. It was run for the first year in straight speed-based staging. Their operating cost was over $30,000 per year just for the pumps. The second year, they turned speed-based staging off and turned best efficiency staging on. They dropped their pump operating cost by over $10,000. Now, yeah, maybe $10,000 isn't a huge amount of money when we look at the total energy consumption of a building, but it's $10,000 that goes right back into that owner's pocket. And if you look at the red bars on this graph, the red bars are actually the load profile for the building. So you notice that in efficiency-based staging, I'm spending an awful lot of time where I'm running two pumps at reduced speed to meet the same connected load as I would with one pump running at full speed. So one thing I hear all the time is, well, this sounds really great, but it also sounds really expensive to implement. Well, we've made it easy. Our MPC controller makes this very, very cost effective and very, very easy to implement. So the MPC stands for modulating pump control, and it is a touchscreen interface that replaces the standard drive keypad. And with this touchscreen interface, it gives you all kinds of information. So as you can see here on the screen, it gives you all the operating parameters. It'll tell me the flow, the head, the speed, the power, the applied voltage, and also the motor current. It also tells me the pump tag and all kinds of other things that it's capable of doing. You can select the units. So if you want to read head in PSI instead of feet, or speed in percentage versus RPM. Power, you can read in kW or horsepower. So you can select all that. The screen is password protected, so not anybody can just walk up to it and touch it and do anything to it. You can also connect to it via Wi-Fi, which is kind of nice for setup, which is the preferred method of setting it up, is to go through the Wi-Fi interface, which I'll show you another screen here in just a minute. And the nice part is that parallel control that I just got done talking about is embedded in this controller. So it doesn't take anything in the way of the BAS to write any fancy sequencing. All they have to do is send the pumps a start-stop signal. And these can all be connected back to the BAS via BACnet or Modbus. So they've got flexibility. They can read everything that's going on, but they don't have to do anything other than tell it it's time to run. So when we look at this, we've got different pump types. So we've got pump control, and you see another thing that says auto flow balance. We'll talk about that in a minute. And then you've got different pump control types, and most common is going to be parallel. Okay, so you're going to set up parallel pumping. When you set up parallel pumping, you've got different control modes that you can set up. One is quadratic. That is a straight line. That's a straight quadratic equation. There's also linear. There's a constant flow mode, a constant head mode. The one that I see most often is either minimum quadratic or minimum quadratic min max. Those are the two that are the most common. And minimum quadratic is you define a predefined minimum speed. So if you're doing like variable primary, chilled water plant, and you know what your minimum flow has to be, you can program in that minimum flow and that pump will come down to that minimum speed and it's not going to go any slower. Okay. Same with min max. If I know what my defined max is, I can set that min max and the pump will operate between those two upper and lower limits. So as we talked about, we know that we have, as engineers, we design a system, we do our head loss calculations, and it is our best estimate of what the actual system head loss is going to be. Well, if the mechanical contractor changes the piping a little bit, things get done differently, buys different equipment, maybe that head loss isn't what you thought it was going to be. The reality is when that happens, I have to recalibrate that control curve to match the system as it's actually installed. And this is what autoflow balance is designed to do. When I enter in autoflow balance mode, I'm going to program in, and it's already going to have it known as what the design flow is. And you're going to open all the control valves in the system, and the pump's going to ramp up, and it's going to figure out what the maximum head is at that design flow, because it's going to come up until it hits the design flow. So let's say it's 1,000 GPM, and you designed it for 100 feet ahead, but it was able to hit design flow at only 85 feet ahead. So it marks that number, and it's going to ask you to close all the control valves. And it's going to slow that pump on back down, and it's going to figure out what the bottom end or that minimum control set point is. Now it's going to come up and it's going to ask you, hey, here's the new values. Do you want to accept them? You tell it yes. And now you've recalibrated the control curve to match the actual system the way it's installed. Okay, this recalibrates that self-sensing algorithm to the site conditions perfectly. The nice thing is, if something ever happens that the building changes, you add an air handler, you add piping onto the system, you do an addition to the building and you use the same pumps, now I can go back and I can recalibrate based on the new conditions. How many times do we design a system that we put pumps in knowing that there's going to be an expansion, but that expansion may not be for a year or two? So you need to calibrate it for the condition at that point, but you need to go back and recalibrate when the building addition gets put on. So what this does is that recalibrates or readjusts that min and max head for the quadratic control curve. And it does it easily. I can do one in about 10 minutes. That's how easy it is. Okay. So I told you there was a Wi-Fi dashboard. So if I connect to that pump via Wi-Fi, I get a screen like this. And it gives me all the parallel information. So across the parallel information, it tells me the head, the flow, and the horsepower in parallel for all the pumps that are operating. And then below that is an individual pump screen. So if I'm looking and connected to chilled water pump number 1, it's going to give me the flow, the head, the power, everything that it's seeing at that point in time for that individual pump. And then down below, of course, is your pump and system curve. And normally there'll be dots on there where the pump is actually operating at. On the dashboard, it also gives you alarm information and warning information. And this is what you use. You see the bar over there on the left-hand side for data and settings and all. This is where you can do all the configuration for the pump. You can also do it from the keypad, but it's cleaner and easier. It's a little bit faster to do it through the web interface. So let's talk a little bit about parallel pumps and what this is all about.
Hey, Tony, before you go any further, Bill's asking a question, and I'm not sure anyways, it says, explain how or if you trim the impeller with MPC pumping.
So in today's world, when we move into self-sensing control, we don't have to worry about impeller trimming, because what we're going to do is we'll just set the pump speed to deliver the design flow at whatever the design head, whatever the actual system head needs to be. So I don't have to worry about trimming impellers anymore. We'll design the pump when you do your initial pump selections. We'll design it for whatever impeller is required to meet the design flow and head. And then when it gets out in the field, if you need to, we'll just run it at a slightly slower speed.
10-4.
So when we look at parallel self-sensing pump control, it's really about understanding efficiency and using best efficiency staging. It's about capitalizing on the embedded logic. You don't need a PLC, you don't need the DP sensor, you don't need the BAS guy to program anything, okay? You know, we're pump guys. We know this works. This is what we do every day. And it's been factory tested, which means that you're going to get faster startup and you're going to get lower risk. And who isn't more happy when they get lower risk, right? This is great. So if I look at this, the other thing I got to be concerned with is redundancy. And yes, that is my high school graduation photo. One thing we've always done in the pumping world is we've done duty standby. So we put 2 pumps in, each sized at 100%. And that really doesn't get us what we need. Yes, it gives us redundancy, but it doesn't give us the energy efficiency we need. So what I want to talk about is how do we get to where we need to be? So we know that HVAC systems are designed to have a backup most of the time. When I look at pumps, redundancy is a little bit different. So redundancy is the percentage of system design flow that is available when one operating pump fails on a design demand day, or N-1, okay? Where N is the number of pumps in the system. So redundancy percentage is equal to the flow rate at N-1 divided by the design flow. So if I look at this, kind of have to understand a little bit about parallel pumping. So in parallel pumping, when I have a parallel pump curve, my flows are additive with both pumps running. The head is whatever the system head is at that design flow rate, but the flows are additive. So when I look at this, what I have to understand, that's my design point. And there's my system curve. The thing we have to understand with parallel pumping, all pumps must be identical. I can't have different size pumps. It's not going to behave well.
So
okay,
that leads me to Jacob's question. If you have 2 loops that have different flows, do you then recommend a DP sensor? And obviously, I think based on that statement, the answer is yes.
Yes. Self-sensing works in the vast majority of applications, but there are piping scenarios where you have different loops with different head requirements that, yes, you still have to have a sensor in those locations.
And Chris made a great statement, at least I think it's a great statement, and I pat him on the back, and maybe you will too, Tony. Sounds like there are no negatives to self-sensing pumps.
No, there really aren't, and that's a great observation.
Yeah.
You have to understand your system design though.
Yeah.
So,
and then Bill said, do you ever run over 60 hertz if you need more pump without exceeding FLA? That's a touchy one.
Generally speaking, the way pumps are designed, unlike fans, because the way pumps work and the way the casing and the impeller is all designed as a system, generally we don't really go over speed a whole lot. I've seen some pumps operate up to about 62 or 63 hertz, but that's about the upper limit that we tend to go to.
Yeah, I always recommend and tell people, if you want to go above 60, contact the rep/factory. I don't care whose pump it is.
Yeah, I don't recommend it. I've had a couple of jobs where I've had to go to 61 or 62 for a very narrow band of operation, but I don't recommend it on a regular basis.
Yeah.
So anyway, so our parallel pumps, so they got to be identical, okay? And that what we have to understand is that each pump is operating at its own flow, its half flow rate on its own individual curve, okay? So we have to understand that, but what we have to understand is the motor has to be sized for when that single pump is going to come out and cross the system curve. So we've got to make sure the motors are sized for that that operating point with one pump on. Otherwise, we get into a motor overload condition. Okay. It's also critical that the system curve intersects in a parallel set where I've only got 2 pumps in parallel. The system curve has to intersect both pumps. When I move into 3 and 4 pumps, I have to understand what my minimum is going to be to know how many pumps have to cross the system curve. Okay. So keep in mind that motor is sized for that single pump operating point, so we don't get into an overload condition. So what happens? How does this, where does this redundancy come into the picture? When you have intelligent controls on the pumps, if one pump fails, the remaining pump will increase speed to the max motor speed and motor capability. So we're going to come out and we're going to allow that pump to run out to where it hits the system curve at that max speed, which is generally, if I size two pumps at 50% each, that's generally about 70 to 75, maybe 80%, depends on the exact pump, of the design flow. And you're thinking, well, okay, I get that, but that's really not 100%. That's not really full redundancy. Well, it's 70% redundancy, okay? So if I do the math, that works out to 70% redundancy because I'm 70% of my design flow. Well, what does that really mean? So let's look at a couple examples so I can kind of give you a better idea. So if I look at a KS 4011D vertical inline pump, size for 1,000 GPM at 80 feet ahead. If I put two pumps in, each size for 50%, so I'm doing 500 GPM per pump, I've got 70% of redundancy. Okay, that's what that pump is going to deliver at, if it's just one pump and it runs out to full speed. That's what it's going to deliver. However, if I look at that same setup, I can drop my motor horsepower down to 10 horsepower. Okay, now what I'm going to get is, are you ready for this? In this scenario with three pumps in parallel, so three pumps are handling the entire load. If one pump of that three fails, I can deliver 910 GPM or 91% of the design flow. So as you can see, if I go from two pumps to three pumps or even four pumps, because that MPC is capable of operating up to four pumps in parallel. And I can do three pumps in parallel to standby, or I can do four pumps without a standby. So however you want to break it up. But the advantage you have is if I do three pumps, each sized at 33%, now if two pumps are operating, so N minus one, now I've got 91% of my design flow. Okay, now I know everybody's saying, well, that's still not 100% of the design flow. So if I look at this in summary, 2 at 50% gives me 70% redundancy, 3 at 33 gets me 91%. This is why this is important. We all know the heat transfer formula, that BTUs equals U times A times LMTD, where U is the heat transfer coefficient of your coil, A is your surface area of the coil, and then LMTD, of course, is the log mean temperature difference. This chart is straight out of ASHRAE, straight out of the ASHRAE handbook. I didn't make this up, I promise. So if I look at this, if you look across the horizontal axis, that is the percentage of design flow rate. If I look at 80% flow, I'm up above 90% of heat transfer. So what that really means is that for a heating coil, at 80% flow, I can get 98% of the heat transfer out of that coil. And at 80% flow, I can get 95% of chilled water coil capacity. Now, we understand that HVAC systems are part load systems. So understanding the redundancy equation and how much redundancy is really important is critical to understand what we need to do. Are you designing a school? Are you designing an office building? Are you designing a hospital? Or are you designing a data center? Because all of those have different redundancy requirements. Think about when the load is going to occur in a school. You know, most of the time, kids are out of school in the summertime. So when's a design day happen? Most parts of the world that I know, at least in the US anyway, design days happen in July and August. Kids aren't even in school. Now, maybe they are at the end of August. But even then, is the school building ever at 100% occupancy? Usually not. So understand where redundancy is important and allow it to help guide you on your pumping design.
By the way, Bill, Bill says you get about 80% of heat transfer at 50% speed. He posted that just before you went to that screen.
Yeah. So and I think this is the thing that people need to understand, Brett, is that, you know, understanding redundancy and how redundancy affects your system really has to play into how we select our pumps to get the best efficiency out of our pumping system. Okay, getting the best efficiency out of the chillers and all that stuff is easy, but what do we do on the pumps? How do we get there? And this is what this is all about. And so the other thing we have to understand is we have to understand turn down, especially if we move towards all variable systems. We've gone by the wayside of a primary secondary system with a constant speed primary and a variable speed secondary. I don't see those very often anymore. I'm seeing more all variable systems. So I've got variable speed primary and variable speed secondary, or I've got a variable primary. We don't even have secondaries anymore. What we have to understand is that in that scenario, as we start to slow down and come down to minimum load, if I've got duty standby pumps, I can only turn down so far. I can turn down to about 30% of BEP flow. So in essence, what that means is I've got about a 4-to-1 turn down out of that single pump. Well, if that pump is producing more flow than what my system needs, I've either got to have enough 3-way valves out in the system to handle that flow, or I got to have a minimum flow bypass valve, which means I'm sending more water through the chiller, which means the chiller's not going to be able to slow down, or the boilers aren't going to be able to react well enough, and I'm not going to get the maximum turn down on the boilers or the chillers. Whereas if I put 2 pumps in, now what happens is now I go to an 8-to-1 turn down. Okay, so I'm doubling my turn down capability, which means I can handle a much lower flow, because my 30% of BEP flow, that doesn't change any, but it's 30% of BEP flow of one pump, not the system. So now I'm gaining even better efficiency over that entire load profile by having more turn down capability, as well as the accuracy and everything else that we need. So to sum all this up, as much as I'd love there to be a silver bullet for pumping system design, is dependent on lots and lots of different factors. And we as engineers, we have to take all that into consideration. And that's where having a manufacturer like Taco that you can rely on is a godsend, because we can help you figure all this stuff out, because we can run all these different scenarios and figure out what makes the most sense. Okay. In almost every case that I've ever looked at, parallel pumping has ended up being less expensive, more efficient, and has a smaller footprint than duty standby, because the pumps are going to get smaller. Hopefully, one thing you've taken away from this today is that parallel pumping yields greater redundancy. And hopefully you understand better what happens when we have pumps in parallel and where they're actually going to operate if one pump out of the parallel set fails. Couple all this with the staging strategies that we have developed can further increase your operational savings associated with parallel pumping, and get away from straight speed-based staging and allow us to do efficiency-based staging with all that technology that's built into the VFDs. Mr. Brett, questions, please, sir.
Go back to that screen you just had. Someone's asking, and I think I know the answer, but I want to make sure. Based on that picture, it's not just for our MPC isn't just for verticals. We can also offer it, or TACO also offers it for the base mounted pumps as well.
Yes, I forgot to mention that earlier. Yes, this is available for base mount end suction and vertical inline, either one.
Nice, nice. And then it's a statement, and I'm sure you'll expound on it from Bill. We always make the pump non-overloading in VFD with enough capacity to match motor horsepower. We have run both fans and pumps over 60 hertz if needed. Had no problems. Lucky you, Bill. We still don't we still cringe whenever it happens.
Yeah, the problem is depending, what you got to remember is that as you increase speed, okay, what's the head doing? So the head's going to move up exponentially. And what usually happens is you move far enough right on the curve that your head's gone up because you're running over speed, so you're trying to move more water, and your head's moving up faster than what the speed and the flow are going up. So you end up running out of pump much quicker, and you get to the end of the curve, and once you get beyond that maximum allowable, you start to get into an unstable area of the curve. Okay, and bad things start to happen because you're starting to change the thrust allowances on the impeller, both the radial and the axial thrust that are happening to that impeller inside that casing. And that's the one thing that is different with pumps and fans. Fans behave a little bit differently when you go to overspeed. You don't get the same bearing loading.
That's about it for questions, Tony. I think you covered a lot of ground. If anyone has any other questions, pop them in. But other than that, I think we are. You can go to that last screen now. I like that one.
Oh, my million hands.
Well, let's see. 2, 4, 6, 8, 10, 12. 12 hands, but maybe more question marks, right?
Yeah.
Okay, wait. We got another question here. Hold on. Let me expound. Done a lot of heating and domestic water systems with VFDs. If we need 2 pumps, we add an installed spare. So 3 pumps, etc. I have found if you don't install the spare, it gets lost and won't run. I fully agree. If you want to do parallel pumps, yes, yes, you're going to do parallel pumps, but you want a third one just in case. Yeah. And
that is my preference, Brett. Is either 3 pumps in parallel with 2 operating and a third standby. Because in that case, if you've got that third standby, now you have 100% redundancy because you're always going to have 2 pumps available. And if you need the greater turn down range, okay, you can always go to 4 pumps. So 3 operating plus the 4 standby, which is going to drop your motor horsepowers down. You're going to get smaller pumps, which decreases your wiring costs, and your piping, your pipe sizes are going to drop because your drops down, your pumps are going to get smaller. So there's lots of reasons to why parallel pumping really starts to make sense.
Yeah. And then Michael says, good explanation on overdriving the pump as opposed to fans. I overdrive the VFD on fans all of the time, but not on pumps. Thanks. So,
yep.
Fans and pumps are different, but that's for sure.
Yeah.
Yeah.
It radically changes the radial and axial loading on the shaft when you start to overspeed that pump. And so it also causes discharge and suction recirculation issues. There's a whole host of things that actually happen as you overdrive that pump.
And I want to
go down below its minimum speed too.
I want to emphasize something Tony said during his presentation, and it's critical for design engineers and all of us in any industry really. But you need to know what the project is, what the building is, right? There's so many different jobs you folks, we all get involved in, and some have different requirements, right? Like a data center compared to a school, and So design around the project first and foremost, and then take into account all of these details that we cover in a lot of these webinars. I can't emphasize that enough. You got to know. Not every system is for every project, to be quite honest.
Exactly. HVAC, as much as some people like to think it is, HVAC design is not cookie cutter. Every building is different. Every owner has different requirements, and you have to fully understand what the owner's project requirements are and how you're going to meet them.
Yeah. And this is funny, and this is so true. I have seen many jobs where you come back 2 years later and all the pumps are in hand.
Oh yeah,
that's another whole subject.
Oh yeah.
Yeah, if you design it too complicated, that's what's going to end up happening. I mean,
Oh yeah.
it's crazy.
Well, and Brett, I think that's one of the things that I like about self-sensing. And we can do self-sensing with or without parallel control. Doesn't make any
Right.
difference. It's
Yeah.
But
Yeah.
the advantage to self-sensing is I don't have to worry about that differential pressure transmitter getting put in the wrong location. And I don't know how many jobs I've gone out and it's in the wrong spot. It's too close to the mechanical room, or it's at some location that was convenient for the BAS contractor, but not the right location for the system.
I actually think
And
there's folks that go to job sites and they've created their own business model, and they understand where the sensor should go. They see it's in the wrong place, and they make these suggestions and get paid to tell people where to put it correctly.
oh yeah, my son who's an engineer does commissioning for a firm, and he goes, that is the single biggest problem that he sees on hydronic systems is the DP sensor is in the wrong location, but he never has that problem on a self-sensing job.
Yeah, because it's in somebody's pocket.
Yep.
Doesn't need to be out there. Well, great job, Tony. I don't see any other questions. So if you want to say goodbye, and then I'll sign us off, you feel free.
Thanks, everybody. I appreciate your time and attention today, and look forward to the next one. Thanks, Brett.
Thanks, Tony. Great job. Rich, you want to say goodbye? You still there? You want to say hi and bye? All right. Other than that, we will see you in a couple of weeks. I think the next one's 2 weeks from today. Enjoy the 4th, and if you're going away, be safe, have some fun. And other than that, take care, everybody. Again, the handouts were available. Excuse me, there was one handout. Hopefully you're already downloaded. If you don't, send us an email and we can send you the slides. And then 24 hours, you'll get the info on the recording, as well as your PDH certificate. Take care, everybody. See you again. Bye.
See y'all.